Okay, so now we're on to the offshore wind and related topics. The first to present is Edvard. Today he'll be talking about the advances in wind blade coating and testing. He's an R&D manager at Carboline. He had a bachelor in chemistry for OIH Norway. He's had 43 years experience in the coating industry. The last 20 years focus have been specific to wind turbine blade coatings. He's a chairman on the Norwegian Society for Paint and Varnish Technology, and he's the president of Federation Scandinavian Paint and Varnish Technologists. Let him go.
I was the president, not anymore. Okay. It's okay?
Yeah.
I will start with our company, or the owner of our company, RPM. Probably three letters that you don't know. Is there back? Okay. Carboline is owned by RPM, founded in 1947. We are, I will say, hundreds of companies. I will show you a little bit later, not going into details. If you are on the New York Stock Exchange, you know RPM. If you are not there, you're probably not familiar with the company. I will show, okay. There we are. I'm too fast, or this one is slow. There we are. An overview of what RPM is. We are divided into 4 divisions, segments, where Carboline belongs to the upper right part here, the performance group. Mainly means protection of steel, concrete, and other substrates. Carboline in Europe, when you look on manufacturing and R&D, we are in Spain, in Italy, and in Norway. The global headquarters for wind blade coating, both development and manufacturing, is in Norway. And the reason for that could be that we are close to Denmark. Denmark is the cluster and the most important country. When it comes to wind power, it started 30, 40 years ago, and we went into this industry because we had a customer asking for a product that we didn't have. So it was my duty to develop that product, and since then we have had some success in this industry. I think you have seen this graph already today. And when you see the part of what wind and electricity is, it's just a few percent. Actually, 20% is electricity, and something like a quarter of that is coming from wind. You can see it's quite easy to find nice graphs, photos, when you are making a presentation here. DNV, as I use a source here, has hundreds of data available for you. I will not go much into that, as already been shown here previous today. If we look on the blade coating, what we will focus on today, this is saying something about our market, how this market is growing. It's hard to find exact data because the manufacturer of turbines do not tell you about turnover, but they tell you about installed capacity. And there's a relation between the installed capacity and the area to be coated, both for the blades and for the towers. And you see it's growing, and it's growing also because of the size of the blades are growing. Basically, this is how it looks like. I think you have seen it all before. And to need the coated area is mainly the blades and the tower, and I will only focus on the blades. Okay. So what's the similarities between steel and blade coating? Most of us has a history in corrosion protection and steel. We are doing the same. We are protecting a surface from different environment. On steel is corrosion, on blades is mostly erosion. And the goal is to increase the lifetime of the object and also to make the blades more sustainable. Longer lifetime means more energy and less repair, although that will be a topic later today. In the end, what's important here is to prevent the loss of energy. The annual energy output from a blade should be as high as possible, and to do that, you really need actually to maintain it. And next speaker, or later on, he will say something about that. In the end, okay, the problem is I don't see the same on the screen. It's where is this? Yeah, preventing loss of energy, important. It can be up to 3% because of the surface is not as smooth as it should be, or the edge has been damaged. And in the end, we also want to give some colors to the object. Not most interesting color we use is gray or white and a little bit red. And in this photo, we here it's no, that was not the right one. Yeah, it was the top one. Okay. Anyhow, eagles can be a problem. Eagles cannot see blades. That's why that single blade was painted black. And the only thing that we don't know about it, we haven't asked the eagle, does it give it an effect or not? That's another project. So steel production has been, we know what steel is, and we have been coating steel for 100 years. And this is a fixed installation. When it comes to blades, they have been made commercial the last 20 years. The building material is partly known, but for a coating manufacturer, we don't get the whole composition. It's a lot of secrets in this business, and a blade surface is not defined by a standard as a steel is. And third, the object is moving at a certain speed. If you see on the development on turbine size, when does it stop? Now the record is 115 meters, close to 1,000 square meters that need to be coated. This is how blades are made. Just made it simple. You glue it, or you make it in one spot. A little bit more complicated, but give you a stronger blade, according to the manufacturer. But the most of the blades that are on the market is actually these bits and pieces glued together. It's more economically, and it's mainly also used onshore. Everybody is talking about offshore, but more than 90% is still onshore. The resin is mostly epoxy. We know epoxy from the coating industry. But I will guess 20% of the blades are made of polyester or similar material, vinyl esters. There's one manufacturer that actually believe in this method, that they have made 400,000 blades, so probably it works. And there are somebody coming out on the market with polyurethane, still not a huge success, I believe. But all of these blades need to be coated with a coating system. Here is typically 2 coating systems. The first one for the system with, it's not there yet. Okay. There it is. The system with a gel coat is most commonly used, and the gel coat or in-mold coating is actually, as I said, is in the mold, and the next coat will then be a top coat. Polyurethane is mostly used, either sprayed as a solvent-borne or rolled as a waterborne. And this tendency to go to waterborne and rolling is a little bit strange because we have been spraying paint for 50 years and more and think this is the best method. Suddenly somebody say, okay, now we want to start rolling. Why do you want to roll a blade that is 100 square meter? No, 1,000 square meter. The only reason for that is that if you spray, you need to have a spray boot. A spray boot that is more than 100 meter is pretty expensive. So why don't you start rolling? That's why you start rolling again. You can discuss the quality, but that's another question. And in the end, it will be a leading edge protection. It's a special topic. I will come back to that. A system without a gel coat has normally both a putty and a primer, and then a top coat and a leading edge protection. For a coating manufacturer, we prefer the last one. It gives us more volumes. We are still a commercial company selling paint. But it's a process that is more expensive, and it's a lot of handwork. When you are looking on the manufacturing on blade, you can be surprised that there are so many people involved in the process. That is also a reason why this industry slowly is moving out of Europe, because of cost reason. Denmark, which was the biggest country, has nearly no manufacturing of blades left. They are partly moving to UK, Southern Europe, to Turkey, India, China. The transportation is expensive, and it's also important if you want to have a contract in a Western European country, you should have a local content to the project. That means that some of the blades or the coating has to be done in the country where you are. Standardization. That's quite difficult within this industry, as long as the substrate is not precise defined, and the competition between the blade manufacturer make it quite difficult to have these parties in the same committee. So today we need to rely, or in our reality, the blade manufacturer specification is more important than ISO standards. Oh, good idea. Then I can see what's come next. So here are some examples on the requirement for a top coat. Quite normal for a paint, but I will go into the rain erosion, which is the topic of today and has been maybe for years and years. There is an ISO standard, slow working, unfortunately. I will not go through those, but there are actually 8 parts, or proposals for 8 parts. And unfortunately, the blade manufacturer do not look into these standards. They keep their own standards. That's the question. Why do we don't find these references in the standard? Because each blade manufacturer, they believe in that they know better than the standard. And this is also about history. quite difficult to change paint specification products. This photo is the most famous one when it comes to erosion of blades. I don't know when it was taken, more than 10 years ago, but I will also use it here. This is what's happening if you are not maintaining your blade or if you don't have the leading edge protection that you need. You can see the coating is gone and partly the laminate underneath is damaged. This will lead to two different things. One, in the end, it can be a total breakdown of the blade, or you are losing the energy output mainly. And the leading edge is a very small part of the blade. I will say that there are, yes, there are some square meter, but in percentage, I believe it's less than 1% that get damaged. How to test this? This is a rain erosion testing rig developed actually for testing helicopter blades, and in daily speaking we call this the helicopter test. It's a rotator, high speed, and there are several models, and it has been developed during the last 50 years or more. The first sample we ever made was actually sent to US, Dayton, University in Dayton, for testing. Then the blade manufacturer was doing their own in-house testing, but they was not satisfied with the testing equipment, and a company in Denmark, R&D, was engaged to find a better method, standardizing. So this is an example for a container solution, rain erosion tester. This is the inside. It's you can see three. There are 600 nozzles where water is coming. Let's see if it works. Water is coming through these nozzles up here, and the sample that you are testing, you are fixing on here, and there are three of this one. You can probably not see the last one. And these are rotating in high speed, and you have water droplets coming from above. This is a specimen. It's not the easiest one to coat, and to standardize or to at least compare erosion resistance, we use a metal. Coating is not very reliable to use a standard, so metal can do. DNV are engaged in this one for standardization. And the speed here, tip speed, is actually close to 160 meters a second. The droplet size is 2.5 millimeter. And we have the possibility to change the droplet size. Then you may have to change 600 needles. So normally we are testing at the standard one. The water flow is 60 liters an hour. The temperature of the water is stable, and it's a photo documentation. Every 10 minutes or every 20 minutes, the machine stops and you take a photo. In the old days, we have to remove all the samples, record them, take a photo, and back again. This is an example on a top coat. We've been running for 2.5 hours. And you can see that there is a damage up here. The rest is perfect. This is quite normal that we get some damage on one and the rest is perfect. To apply a product without any pore can be difficult, and if you have a porosity in the material, that can show up as a damage here. This is a two-way of erosion modes. The first one to the left is actually a top coat. The other one is a leading edge protection, and typically for this kind of soft material, if you get a damage, it will get damaged very fast. So it can be a huge difference only within 10 minutes. Time is running. So this is the kind of material you use for protecting the edge. It can either be a tape or the newest one called soft shell. We are more into liquid coating, and this is a high viscous, normally solvent-free polyurethane. The idea behind is that the energy created by when the water droplet is hitting the surface need to be absorbed. So if you have a rubber-like material, it will absorb the energy from the water, and the erosion resistance will be much longer normally than a harder material. The theory is there that to make the perfect product, a liquid one, is quite difficult. So what we get from here, we get a lot of information on the erosion resistance, but all the system and the needs, it's hard to test all these parameters. We are focusing on top coat, but still it's a system. And it can take you 5 hours to test along this rain erosion or leading edge product. And if you want to take it in a system, it takes weeks and hours, weeks and weeks before we actually are finished. I don't know how many tests we have done. We have been doing this for 10 years. The last model is 2 years. So the liquid LEP, as we call it, it's a polyurethane. It's either a polyurethane, normally 2K, it's a polyaspartic or a polyurea, and all this kind of material, they can absorb energy. The drawback is actually, it seems that the most flexible material, the softest material, can absorb most energy, but then is losing some robustness. It's hard to handle. When you are moving the blades in the field, can this material get damaged? They have normally short pot life, but unfortunately not slow, they have a slow curing. It takes hours and hours before they dry. And it's a manual application, although robots are coming, but a manual application, I think that's the biggest issue, that you get the variation in the results. Because nobody can, this is normally supplied in a cartridge, and the operator is doing by his hand with a scraper how to do that in a perfect way. So we are looking forward for the robots that come later today. And as I said, it's a lot of research in this field. There's a yearly conference in Denmark on rain erosion. I was there in February. I think it was 135 people sitting 3 days only to discuss this one topic. And I got the invitation for next year also. So it's a lot of theory. Theories are there, but to transfer that into a material, quite difficult. So what are we doing? We are working together, both the academia, the industry, the blade manufacturer, and we have all the raw material suppliers here. The International Energy Agency, the International Energy Agency is also involved in this work. They giving recommendation. And the main headquarters, let's call it that, is actually in Denmark, the Danish Technology University, DTU. So it's more than rain. We have sunshine, we have storm, we have ice. How to combine this into one cycle or into one test? More or less impossible. But at least what we have started to do is actually to expose this specimen into this ISO cycle. And after 6 months exposure, we put them into the rain erosion test. What is the difference with a new material versus the one that has been exposed for 6 months? They are not the easiest actually to test because of the size and the form, shape of the specimen. And we need to use some flat panel beside. So, summary. This is still a young industry, and it will grow. The question is, when will it stop? Will it stop at 115 meter? Will the next blade be 125? I think a limitation is transportation. These blades can only be used offshore. They can only be transported, let's say, from the factory to the harbor and then with a ship. That will be a limitation. Material is in development. For a coating manufacturer, it's a little bit problematic that we do not have, call it standard, that we are not working on the same standards. It's not like in the steel industry. And it needs to be developed. We have a tendency to look on single product instead of systems. And system takes more time. Blade manufacturer today, he wants to have several products or a system from one supplier instead of buying primer from one and the top coat from another. And the qualification for a product or a system can take 9 to 24 months if you are lucky. I think that's it. There it was, yeah. Any questions?
Thank you for the presentation, very interesting. When you talk about coating the leading edge of the blade and the materials needing to be flexible, how flexible does it need to be? Because there are some fantastic hard-wearing materials out there that we've used for pipe linings and field joint coatings, that sort of stuff.
I don't have an exact number, but if you say elongation of this material could be 50 to 100%. Something like that.
That is definitely another question.
Yeah. But I know that some hard material also works at least as a top coat, but we haven't seen it at this work as a leading edge protection. So far, all the material, if it's tape, it's liquid LED or this soft shell, they are all flexible and they are polyurethane based, and that seems to work.
Thank you.
How thick are the coatings? What thickness?
Thickness from 200 microns and upwards. Even 200 microns can be sufficient.
Okay, anybody else? Another one question? Anybody? I've got a quick one, Edward. Yeah. Conformance to specification must be quite hard to determine. Thickness, pinholes, etc. must be quite hard. It's not like steel, is it?
No, it's not. And one thing is that you qualify a material in the lab. What about a real application on the site? It's and mainly because it's too much. It's a lot of handwork here. But we know that things are progressing. The blades that was made 15 years ago the blades made today is much better than the blades made 15 years ago. Now they know the cost of the repair, and it's tremendous. If you go out in the North Sea to repair, that costs you money.